Started. So welcome everyone. Good evening to our monthly quantitative finance seminar series here at the Fields Institute. Before I introduce our speaker for the day, I'd like to thank Waterfront International and Scotiabank for their continual support of the seminar series through the Center for Financial Industries. And with that, I'd like to introduce our speaker, Professor Jan Obloj. He is a professor, and I know I pronounced that wrong. It's supposed to be Obloj or something. Yeah. I always mix it up in my head. Is a professor of mathematics at the University of Oxford's Mathematical Institute. He's a fellow of St. John's College of Oxford and a member of the Oxford Mann Institute for Quantitative Finance. He holds a PhD from University Paris 6 and Warsaw University. He's also the current president of the Bachelor of Finance Society, and he's a fellow of the Institute of Mathematical Statistics. He has general interest in mathematics of randomness, and his research sits at the crossroads of various fields, including probability theory, statistics, mathematical finance, operations research, optimal transport, and data science. And today, Jan is going to tell us all about optimal OT in math finance. So please join me in welcoming Jan.
Thanks, Sebastian, for this lovely introduction. A real pleasure to be here. Thanks, everyone, for coming. So this is a talk on how optimal transport can be used for model selection. I'll be focusing on calibration. This is sort of a problem in finance, which is of relevance. So that's our focus. But you can sort of think of maybe other contexts where similar issues might arise where you want to select a model. And I'll cover a couple of papers. At some points, I'll stop and try to explain the sort of maths, okay, and then in one context, and then I'll not do this in other context because the maths is similar. I'll just point out what is the sort of, each time you want to do this, you have to work out some other more or less tedious or actually difficult issues, but the sort of underlying fundamental ideas are, I think, common, so I'll try to explain this. And this is based on a number of works with collaborators originally in Monash in Australia. So Ivan is still there, and Greg used to be there, but he's now in Paris. And Ben was a student in Oxford who graduated, and now is again also in Paris because they've are working with Greg in a company trying to make this into an industrial product. And Leo was a student in Monash. All right. So here's a problem. I want to pick a model. Okay? And classically, you would do this by giving yourself a family of models, so maybe indexed by parameter, theta. So maybe those are your Heston models with different parameters. And you do this because you believe it's a good family, it has nice properties, or maybe you can work with it through analytical methods or through numerical methods and compute outputs from these models. And that's what you really want to do in the end. Okay, so you like those models. But you need to calibrate them to data so that they sort of resemble reality. And that means that for some set of market prices, you want your model prices to be close to these market prices, ideally within the bid-ask spread. Okay? So if you have a fixed set of parameters, then of course this is just an optimization problem, and just can hide a more or less difficult numerics in it, or more or less stable methods. But you can sort of think, doing classical methods with it. I am much more interested in the case where I don't have a parametric family of models. So in some sense, I'm happy with any model. Maybe I have some favorite model, and I'll call this P bar. And somehow what I would like to do is say, I want to find the closest model in some sense to P bar, but one which satisfies my constraints. Okay, so essentially, I'm doing some sort of non-parametric projection in the space of, say, martingales. I pick a favorite, say, martingale, which has nice features, which I like as sort of as in the sense of stylized features. So I think that's a good model. But I need it to be calibrated, so I'm going to project it. And this idea actually goes back to late 90s and group of Marco Aveinida. There are nice papers where they were doing this using tools of relative entropy. And we are going to use today general tools of stochastic optimal transport. And I'll try to argue why these are really sort of a powerful toolbox, which allows you to do this in many different contexts. Okay, so that's the program. Okay, so the type of constraints that I will have, just in case there are people who are not familiar with this, I will sometimes talk about, or the motivation came from marginal constraints. And the reason for this is this very classical Brilliant-Lietzenberger type of idea that if you have call prices for many strikes, well, if you differentiate this equality in K twice, you get that this second derivative in terms of distributions of your call prices gives you the distribution of your stock. So somehow having a full knowledge of option prices for one maturity is equivalent to knowing the risk control distribution of stock at that maturity. And so having marginal constraints is quite natural. And if you have marginal constraints, that's where sort of optimal transport becomes a natural language. Okay. So the optimal transport that I want to think about is the Benamou-Bernier formulation. So not necessarily sort of discrete optimal transport coupling measure mu with measure nu, but rather Benamou-Bernier where I think of particles flowing through some vector field, and they start with a given distribution and they want to finish with a given distribution. So I'm optimizing over choice of vector fields. Okay, so it's a sort of continuous time picture where you flow your particles. So you have the continuity equation, which tells you how the distribution of your particles evolves through this vector field, and you want to find vector fields that take distribution rho 0 to rho 1, and then you want to optimize some action functional. And this famously is the same as doing just usual for Wasserstein 2 distance and suitable choice of action F. Quadratic, this is the same problem. So you can go between the static and dynamic, but this is what sort of inspired then the what I'm calling the same martingale optimal transport formulations. Okay, so this goes back to, I think, Mikami and Thielin. This was drift control, and then Nizar Tuzi and Xiaolu Tan had a paper about this stochastic optimal transport control dynamics. In which case, we think about a general same martingale. It has a drift and volatility. I can control or pick both of them. And in this problem, I fix marginal distributions. We'll generalize this in a moment, but think of this as sort of stylized picture. You fix the initial distribution and the terminal distribution, and then you have some cost functional. And it's important this cost functional is of this form. So it's an integral from 0 to 1 or 0 to capital T if you have a time horizon of some functional that depends on your coefficients. It could also depend on randomness. It could depend on your stochastic process. Sort of we can put this lots of things in there. Okay, so this is info over all such processes, and beta and alpha are here adapted processes. So I'm really sort of Ito processes. Okay, and they show that you can. So essentially in this paper, Nizar and Xiaolu show duality. So you can transform this problem into soup. I'll show you in a second how to do this. And once you have this, if you can restrict to sort of Markovian setting, then this becomes a stochastic control problem, and you can get a JB equation. And we're sort of in the game. We can sort of do something and numerically, and that's what we'll be doing. Okay, I'll explain how this works in a moment, but that's the essence of the problem, and then you can generalize this in all sorts of ways. So you can introduce all sorts of constraints. So instead of marginal constraints, you can introduce finitely many discrete constraints, or you can introduce support constraints or some barrier constraints, all sorts of path-dependent constraints if you want. Of course, the more and more involved constraints you have, the harder the problem it is actually to solve, because your dual becomes path-dependent and you have path-dependent PDEs, etc. So it might not be easy to solve, but in principle, we can write some mathematical formulations which are equivalent. Okay. So here's then the brief, rundown of the methodology. I think of this same martingale optimal transport, or more generally, this same martingale control dynamics as a way of inducing a projection on the space of Ito processes or Markov processes usually. Okay, so we gather some market data that's important for us. We fix our favorite reference model P. So that's something that I think captures the dynamics well. And then I want to have some way of projecting it. And using this, this I'm writing F here, but it's really should be integral from 0 to T, F, etc., etc. But I think of this as a cost, and the cost will be infinity if I'm not calibrated, and otherwise it will be some sort of distance between my reference model. Okay, and then we will be able to do this by getting enough convexity to be able to do duality, and then on dual side we'll be solving PDs and then optimizing over a choice of PDs. So that's essentially what we're going to do. And then for the rest of the talk, I want to run through maybe 3 or 4 different problems and show you how this actually works in practice. Okay. So the first problem was a joint calibration of SPX and VIX. Okay. And we picked this up because it was known to be a difficult problem to do in practice. It's sort of, if you just take a local stochastic volatility model, it's not a very easy thing to fit this. And in fact, you do want to do this because, of course, VIX is something that captures market beliefs about the future volatility or 30-day volatility of SPX. So it's intrinsically linked to your SPX, SP 500 and options on it. So the two objects should be, very, very, very related. But it's not easy to calibrate things jointly. So there's a whole literature. I'm not going to do this to go into details, but Julien Gouillon in particular was one who sort of was quite actively arguing that you should really capture them together in one model, but showing that it's difficult. And most people who tried, I think, maybe some of this there are some successes using either models with jumps or models with rough volatility, but all in all, they struggle to achieve an exact fit. It's sort of, I can do a little bit better, maybe I'm a bit more efficient, but somehow it feels there was a question whether you can actually fit those things together using a simple model at all. Okay, so it seemed to be that it wasn't clear. So we said, okay, let's just run this and see what we get. Okay, so let me run you through. There'll be quite a lot of things on the slides, but I'll be just repeating things like I'm giving you, full lists of payoffs that I want to calibrate to. They're there because I think this gets recorded, so I wanted to have all the details in case somebody's watching and wants to read them. But I'll just tell you what matters. What matters is that I have 2 assets. I have S, that's my underlying, and then I have VIX. Of course, VIX in practice is computed by CBOE from options, but let's forget this. It's supposed to be essentially the square root of this conditional expectation of realized volatility. Okay, so that's what this is capturing. So of course, this is derived from the dynamics of S. Okay, it's sort of looking forward 30 days into the future and then taking conditional expectation. And then the options on VIX are nonlinear payoffs of this square root of the conditional expectation. So that's where the sort of difficulty comes in. You can't just simply there's lots of nonlinearities coming through. So we're going to work with x2, which will be the square of the previous process, and x1, which will be log of st. That's just a change of variables. Okay, so those are my two processes. You observe that this process is slightly tricky because at time capital T, it has to be equal to 0. So that's a small technical nuance that I have to somehow achieve. And also, it's today's price is actually equal to one of the futures. So again, there is a little bit of technical issues when you do this in practice, but let's sweep this under the carpet. Okay, so you can go through this, and for some models, you can actually compute dynamics of this process explicitly. That's useful because if you want to have a reference model, it's good to have those processes. So that's just an example. I'm not going obviously to go through this, but just saying that if you take a Heston model, you can compute the dynamics of this the conditional expectation explicitly. That's because it's an affine process, so everything works nicely. Okay, so now what do? I go through this program, so the drift of my process is fixed here. See, the drifts are fixed because the drift of the log of everything is under risk neutral measure, and I'm going to take R to be 0 in this talk, so everything is simple. So the drift of my log stock is just negative half of sigma squared, and also the same happens with x2 because what you're bleeding from the martingale is exactly half of sigma squared. Okay? So there's nothing to do on the drift. The drift is given, and then the volatility is exactly what you optimize. So I'm going to call this beta, this matrix, and that's what you want to optimize. Okay, and then you have some constraints given through your options on the first asset and the second asset, and then you have this constraint of x2 being 0, which I'm going to impose by saying that a certain singular contract has price 0. So essentially think of something that grows extremely fast on both sides, and saying that this is equal to zero expectation is the same as saying that your asset has to be essentially equal to zero. And then our cost function is just the square of my reference value to my calibrated value, and then if the drifts are okay, and if the drifts are wrong, then I put plus infinity. Okay? So that's the problem. So I want to look at the inf. So I project on the all things which have correct joint dynamics. So they have, the today's price is x0. They satisfy all this pricing equation. So this is SPX options, VIX future, VIX options, and this singular contract. So I'm just going to amalgamate this into one vector script G. And I want to minimize this distance. Okay? So that's somehow how I carry out the program. So the first thing that you do, and this is somehow, again, something that works quite generically, is if f is convex, see, then you can, of course, this expectation, you can rewrite, everything just depends here on the distribution of your x, so you can rewrite it in this way, if these are functions of your time and x. Okay, so I would like this to be a Markovian setup. In principle, I don't have Markovian, but see, a simple application of Jensen's inequality tells me that this is, of course, just equal to expectation of conditional expectations, and I can swap this with an inequality because f is convex. So I will need convexity of f to be able to do this. And then this classical Markovian projections, so this idea of generating a Markov process which mimics the one-dimensional marginals of a given Ito process, going back to Gyongyi and Krylov, and really there's a really beautiful paper by Brunik and Shreve where they show this in sort of higher dimensions and including some adapted functionals, tells you that you can restrict yourself to Markov processes. Okay, so you could have, of course, just included this if you want as a restriction to start, but in fact, if you have convexity on f, then this is, with no loss of generality, you can restrict yourself to Markov processes. Now, once you're Markovian, then this expectation there, of course, this is just a function of t and x, and then you have this one-dimensional distributions. So in fact, you're just now optimizing over functions alpha, beta, and rho, just like I was doing in Benhamou-Brenier. Right? In Benhamou-Brenier, I needed to pick a vector field through which my particles were moving, and I had continuity equation, which related my vector field with the density of my particles. And that's exactly what happens here, but instead of the continuity equation, you have Fokker-Planck. You have Fokker-Planck equation, which tells you how the density of your SD evolves. And I needed to change variables. So instead of alpha and beta, I'm considering alpha times rho and beta times rho, because I want this to be convex in rho A and B. And this is not jointly convex. I need to be jointly convex. Okay, so you do a small, you massage things always a little bit to get convexity because you want duality. So that's our primal problem now. So I've completely got rid of the stochasticity. I just now, because I'm Markovian, I'm really now down to optimization over functions that solve certain PDE. So let me now show you how the dual side arises. So this is a dense slide, but I think it's just useful to point that there's no dark magic. It's really just a very natural thing. So all I'm going to do is I'm going to introduce Lagrange multipliers to encode these constraints. Okay, so I have constraints here. So first I need to encode the constraints of this PDE. So I'm going to take phi, which will be my Lagrange multiplier, the function, and this is supposed to be 0, this part here. Okay, and then I have lambda, which is the Lagrange multiplier that looked at the prices of my options in a given model, and then subtracts the prices of the market prices, right? So phi encodes Fokker-Planck, lambda encodes a calibration to market prices. And you see, and that's all, because now you just do min-max, okay? For this, you need some assumptions, so you need sort of Fencher-Rockefeller, so that's why you need convexity. Once you've done this, you recognize that you have f here of alpha beta, and then something times alpha, something times beta. So in fact, inf, so minus sup, and what you see is this sort of dual Legendre transform of f, which appears, right? So this whole thing will collapse, and this inf will collapse, and I'll have a Legendre transform of f here, and so I'll get a PD of this form. DTF plus Legendre transform applied in those points here and here equals to something. Okay, so something on the right is maybe ugly, it's discontinuous, so I need some sort of discontinuous viscosity solutions, et cetera, but that's the PD itself completely, on a sort of on the level of just formal equations, it's really very simple. You just write your Lagrange multipliers and you assume everything works. Of course, then you have to prove it, but somehow there is no dark magic. So that's how you get the dual side, and you see what happens now is quite clear. Also, the other nice thing about this whole type of passive problems, you can of course recover the optimal alpha and beta through the usual relation between Legendre the functions and its transform. Okay? So you get that the optimal alpha and beta will be recovered through the gradient of your Legendre transform at the optimal phi, where the optimal phi is the viscosity solution to your AJB equation. So once you solve the dual side, you can actually read out the optimal model. So then there's this sup over lambdas. These were the Lagrange multipliers for market prices. Okay, so this is something you still have to solve. And on this, you'll just do gradient descent. So you solve the AJB equation, and then you use the AJB to compute model prices. So that's a linear operation. You just do a swipe of the usual pricing equation. You compute model prices, and you look at the difference, and that actually happens to be the gradient. So the gradient of your in which you do descent is precisely the difference between the calibration and the market prices, and then you go and then you iterate this. Okay? So this is your numerical solution. This is not an easy task because in each of the loop you have to solve a nonlinear PD. So depending on how many dimensions you're working in, that's quicker or slower, but I don't have to worry about this. I just need to, deliver a proof of concept. So from the mathematical point of view, it's a tight formula which works. Okay, so I went through this in quite detail because I wanted you to sort of see the steps. Okay, and I won't do this again for the other context, but that was the VIX. It didn't really appear anywhere other than the fact that our F, which we then have to take the dual, had a particular way of penalizing that the drifts have to have this form, otherwise it's plus infinity, etc. So the nature of your problem will enter through the cost function f, and the type of set of the Markov parameters on which it is infinity or not, but the general structure is always the same. Okay. So you get an algorithm, and then you try to do this, and of course it doesn't work. Nothing works in practice. So then you have to do a little bit of engineering. Okay, if you just try to do this, it will not converge. So you have to do a little bit of engineering. One of the reasons why things don't typically converge is that the VIX and the SPX options will be on different scales, and also this thing. So you have to somehow, you normalize your options so that the constraints are of comparable size, and then you also look at the reference model. So I haven't mentioned this at all, but I had some reference. Okay, this was maybe my favorite model. But in practice, what you want to do is typically you take a reference model, you run it for a moment, and then the output, so your current best prediction becomes your new reference, and then you smooth it to become a bit nicer, and then you use it again. That typically produces nicer results. So there's a lot of sort of engineering in getting the method to work nicely, and that's one of the things that I guess Greg and Ben are trying to perfect now on the sort of industry side, but that's more of the sort of on actual numerics. So let me show you how this works. So I think so I'm first we're going to try to reproduce things with simulated data. So I want to have a sanity check. I just generate all my data, and then I check that things work. So we're going to generate things using a Heston model, and then we're going to take another Heston, but with different parameters as reference, and see if we can recover things, etc. Right? So as you would expect, the calibration is perfect. So the red one is the uncalibrated model. So that's your reference. So Heston is our reference, is the wrong reference. Okay, and then we calibrate. And of course, what you see is this. If you look here, you see that the yellow curve, which is my calibrated model, gets pulled towards the reference. And that's because there's no longer any constraints, right? So maybe this is a good moment to sort of stop and realize that this is actually a really sort of powerful framework, but it only does what it says on the tin. Okay, so you told it, here's my reference. I want you to be as close as possible. So whenever your constraints you are not binding, you will be trying to be as close to reference as possible. So if you have a different reference, say in this case reference is just a constant Black-Scholes model, then you see that your vol is sort of sloping down at the very end here because it wants to go to this reference model, and or it does this sort of kink here because it really wants to go to this reference model. So here's some market data. So 26 SPX call options and 9 VIX options, I think, just to be, and you get perfect fit. So this is just, I mean, they're just two Brownian motions here, right? So we're in a pure sort of stochastic volatility like model, and you can get the perfect fit to SPS and VIX. So at least it shows you that there's nothing inherently incompatible with this market data and this type of options. It's just that the models that you get are not necessarily the ones that you would write normally. So if you do simulations, you see that typically there are some sort of phase transitions in your dynamics to account for the different maturities. So if you were to actually plot the vol surfaces that are generating your models, you see that there are sort of discontinuities and quite abrupt changes. But that's allowed. I've never asked in this process, I've never gave smoothness and one of my conditions for being a nice model. I've just told it, here's a model, start with it, and project in this given sense onto a same martingale which calibrates. And so that's what you get. Okay. So I did this in detail with SPX, and then there are other stories where you can do this. Let me give you this very briefly. So this is thinking about what happens when the interest rates are stochastic. This was actually surprisingly, we should thank our referees, because the first paper had we didn't spot the difficulty, and then we spent quite a long time figuring out difficulty. So if you do stochastic interest rates, and of course you have this path-dependent discount factor, and you really don't want to have a path-dependent thing, so we needed to get rid of it, and we thought we'd get rid of it, but there's actually there's some difficulty. So you do Markovian projection, and then you end up with a 3-dimensional object. So your stock, your stochastic short rate, let's say, and then this discount factor, right? So then this is Markovian, that's good, but you want to get rid of this, and that required sort of doing what's known as the superposition principle. So Dario Trevisan had a paper on this. So you somehow have to build a 2-dimensional Markov process, but which has the right 1-dimensional marginals. And yeah, but you can do this. So the bottom line is you end up working with sub-probability measures, so discounted probabilities, and you do the superposition to prove existence of certain mirroring Markov process. So there's more mathematics you have to do, but it turns out that everything works nicely. And then we did this in two approaches. So one approach when the short rate model is calibrated separately. So for whatever reason, another desk calibrated the short rate, and now you have this part of your model fixed, and then you're only calibrating, doing projection of your favorite, I don't know, Black-Scholes, Heston, whatever you want. Heston doesn't work. So something simple here on your say martingales, or we did the joint calibration together. Okay, so the bottom line is, of course, things work. Okay, this is hitting the exactly the values. This was simulated data, and you see that, of course, what happens is that this is the volatility of your stock. So this is the local volatility. I had some reference value, which was just essentially, you can see a surface like this, a CEV surface, and then it was a generating model with a CEV with another surface, and then of course what you end up with something that's in between, because you need to fit the call prices which were coming from this one at some given maturities, but then you want to be close to this reference model. So the reference model becomes important, of course. You want to be as close as possible with fitting things. And the one thing that we've learned from this exercise, which you can't see, I mean, all you can see in this picture is that I have two surfaces which are constant, right? But actually what this is showing you is the correlation between the Brownian motions driving stock and the short rate. And if you think about this for a moment, I was using just caps, so some fixed income instruments and SPX options. And there's nothing that really tells me how the two things behave together. So I didn't have any covariance information. And so I can't recover this. When I do this, I can't recover the correlation parameter. So what this is showing is a good reference and a bad reference, and they just differed by sign of correlation. Okay, so in one, the correlation was positive, in the other one was negative. And all these pictures are showing is that your calibrated model actually sticks with whatever the reference you gave it to. There's nothing in the data that allows you to recover the correct size. So even if I generated data with negative correlation, I can still perfectly fit it with positive correlation if I want to. So then you have to sort of think about what data you want to include. And then we did joint calibration. So this is, you jointly at the same time try to fit the stochastic rates and SPX, and this also actually works really nicely. We had quite a lot of data, I think, here, and this is what you get. And actually, so this is my favorite methodology. In fact, what we did here is the way we did a reference model is we started with some parametric family of models, okay, and then we did parametric calibration. So I think here this was a very simple CEV Vasicek type of combination, okay? And this gives you the red curves, okay. So believe it or not, the red curves, see, on SPX you're very close to being calibrated but on the interest rates, of course, you can't fit things very well. And then you take this parametrically calibrated favorite model as your reference, and then you say, well, okay, now let's improve it so that it calibrates perfectly. Okay. And that's the blue curves. So the blue curves are then, of course, perfectly calibrated. That's what you get from the SOT projection. But because you had something quite sensible to start with, this is actually numerically stable and quite fast. So somehow this really, I think, is a nice way of doing an extra step to improve parametric calibration. Okay, and for reference, I wanted to include characteristics, but they're all in the paper, and you can look at this. Okay, so those are two examples I wanted to show where things were done only numerically. But then, you really want to, you keep thinking, is there some case where I could do things, explicitly, like on paper? Right? Is there a case where I can, is there some sort of case of this, say, martingale projection that I can solve, well, essentially explicitly? That's the case. And that's the martingale-Benhamou formulation. And that's the only case where I think you can do things explicitly. I can't prove this is a theorem, but anyway, I've tried, and clearly that's the only one we can say. So that's the last part of the talk. I'm going to show you cases where you can solve explicitly. Now, I will do this only with marginal constraints. Okay, so I'm back to the case, this sort of conceptually idealized case where my options give me, marginals. So the case you should have in mind is really just calibrating SPX. Okay, so SPX have many options, enough really to extract the marginal distributions, and so you're given marginal distributions. So that's the problem I want to solve. Okay, so we thought, like, what's the most natural problem we can write? So my reference model is Black-Scholes, and I want to calibrate a geometric. Well, you can read here, right? So I'm just calibrating interest rates and dividends are 0. So I'm just having a martingale, and I want to look at martingale, which is closest to geometric Brownian motion in this averaged square sense, but which has given marginals mu0 and mu1. And if I can solve this, then I can patch them together, hopefully, and so I can calibrate the whole surface. So I'm going to call this geometric martingale-Benhamou-Bernier problem. Geometric because I'm obviously looking at sigma. So I have this S here, right? So I'm looking at volatility. And then Benhamou-Bernier because, well, this looks like the functional that we had in the. So it turns out that this you can solve explicitly. So this was the Benhamou-Bernier formulation. I rewrote this a little bit just to keep the very similar notation, but it's exactly what I had on my first slide, except instead of F, now I really have the quadratic form to match my quadratic form here. And then the next set of papers, to an extent inspired by this Xiaolu and Nizar's paper, was an arithmetic version. So if you think about what was just my last slide, the only difference is that instead of sigma S, so I'm using M now, I have this sigma here, which is then my the parameter, the intensity of my martingale here, and I'm looking at this minus some reference value. So it's an arithmetic version. Instead of having a geometric martingale, I'm just looking at arithmetic, and I want to find something that's closest to Brownian motion. So this was a problem posed by Julio Barkov and co-authors and Martin Huisman and Dario Trevisan independently or in parallel. And this one you can solve really neatly. Okay? So let me show you how you solve this and why this has a very simple explicit solution. So you can you take the square, you expand this, of course you get those terms here, and then I have a constant, I have integral of x squared against the so I have this term here, but this term is just equal to the quadratic variation of my martingale, which is then equal to the difference between m1 squared and m0 squared, but those have given marginals, so that's again a given constant. So those three terms are given, and what's left is just this last bit here, which is the cross term. So I had a sigma bar here in front, which I took out. So essentially the equivalent problem is now maximizing this integral from 0 to 1. And just like in Benhamou-Bernier, in fact, you see that this sigma bar, the reference value, completely disappeared. So you want to be closest to a version of Brownian motion, but you don't really, the level, you want to be constant, not volatility, but let's, the martingale density with respect to Brownian motion, you want to be constant, but you don't, the level will be adjusted accordingly to your margins. So what is this? This is, of course, covariance. This integral from 0 to 1, sigma t dt, this is the same as MB1. That's the quadratic covariation between a martingale and Brownian motion in time 1, which then is equal to, so if I take expectation, this will be expectation of M1 B1 minus M0 B0, and then if I do conditional expectation, I end up with the value with the expression on the right. And this is neat because, see, I've completely lost the dependence in time. Just like in Benhamou-Bernier, I'm now considering a static problem of coupling between the terminal value of my martingale and the Brownian increment. This has a Gaussian distribution, so I'm just coupling a certain distribution with a Gaussian distribution. I know how to do this. This is just the Bernier theorem. I know that this has to be an increasing function of this. So I can write this. M1 is an increasing function of B1, maybe depends on B0. So now there's a little bit of work to do because I have to find the distribution of B0, which works nice, but there is a choice. Let's call it alpha, such that this f is independent of b0, and then you see that m is just equal to f of b1 and then conditional expectation. So everything is explicit. Fm is an explicit given function. F, right? So if I think about this, then I get that mt is equal to expectation of f of b1 given ft, and this is the same as expectation of f of b1 minus bt plus bt. So this is measurable, this is independent. That's why I have the convolution with a Gaussian kernel with variance 1 minus t. Everything is neat. So this was done in those two papers I've mentioned. They, we can figure out everything. This is known as the Bast martingale. And now you just have to compute this alpha. So there's choice of alpha that this is independent. So you have to somehow find this, and you do this by a certain fixed point problem that I'll introduce in a moment. So now I'm going back to my geometric version. This was what seemed more natural in case of finance. Okay, so the only difference again is that instead of having here sigma u as u minus a constant, I have this sigma t minus a constant. Okay, so but the same thing works. This value function, if I expand this, or if I do eta on it, I see that this is the same as the value of the log, or twice log of s0 minus s1, and those are given. Okay, so this first part, if I expand the square, is known. This will be a constant, so it's just the cross product. So this problem again is equivalent to the problem of maximizing this integral. That's where I run out of my luck. I can't do this anymore. So I can't relate that integral to just something that's related to the terminal value of my martingale. That breaks down. This is this magic of this one expression only, I think. But we can do something, okay? So I can do the following, right? So this is my expectation that I'm interested in. I'm going to change measure. I'm going to change measure with ST. ST is a martingale, so I can change my measure, and I have now P tilde is a measure defined using my process that I'm looking for. I'm going to use it to change the measure. Okay. So if I do this, then this is expectation under P tilde of 1 over ST, this integral. But that's great because this is a martingale under P tilde, so I can pull it in and I get that. Okay, so I'm going to call this sigma t, capital sigma t. And I'm going to look at the dynamics of my martingale, RT, which is 1 over ST, under P tilde. And if you do this, you see that this is exactly, it has these dynamics. Okay. That's just Girsanov where you put the drift. Moreover, if you look at the expectation of some function, test function of g of R1, that's the same as the P expectation of g of R1 times S1, so divided by R1. Okay, so this is this quantity here. So that's something that's given explicitly in terms of mu1. So in fact, you see that under P tilde, this process R has a fixed marginals at time 1 and 0, which are obtained through this somewhat maybe unusual, but transformation of mu1. Okay. So now I'm in business, see, because what I can do now is so I will introduce this transformation. Let's call it F dagger. I'm really interested in this identity dagger. So it's I first change the density of mu with a y, and then I push forward 1 over y through this measure. Okay, so this is exactly what's happening here. I'm just doing this. I'm calling this, giving this a certain name. It's an involution operation if you assume that measures are centered or have mean 1. Great. So now you see that I have a full, and I can go back. So whenever I have a candidate process for my geometric problem, for my measures mu0 and mu1, I obtain a candidate problem for my arithmetic problem, but now with marginals mu0 and mu1 and back. Okay, so I can actually show that the two problems are equivalent, and moreover, I can really relate the optimizers. So if I have an optimizer for my problem, which I know I have, which was precisely of this form, then I can obtain the optimizer or the distribution of the optimizer for this. And this optimizer was unique in distribution, so this one is also unique in distribution, etc. We're in business. Okay, great. So as it turns out, with a little bit of magic, and this idea of changing numeraire in optimal transport was also explored in a paper in discrete setting by Luciano Campi and co-authors. You really can solve this. So in fact, we can solve both this and this explicitly. And you can get the dynamics. So you really your volatility coefficients, you can get them explicitly, everything, and you can generalize to some other slightly more general cost functions, etc. And you can also ask yourself, when is it that the two problems coincide? You know, in principle, I have different problems, but maybe the optimizers are the same. And you can show that they are the same if and only if you're log normal. So unless if your Vol surface is constant, then yes, you have the same dynamics. Otherwise, you have different dynamics. Okay. And I promised that there is a fixed point. So there's this fixed point which we called. This was first done by Pierre-Henri Labordère and Coles with the when they really looked at the fixed point problem. You can write it as a two-step problem, and then it looks like a martingale version of synchron algorithm, and it's really very fast. Okay, so you really can solve this. You need to solve for alpha and f, right? So this equation, if you see what it reads, it says alpha is my initial distribution of my Brownian motion. Maybe here, alpha is my initial distribution of my Brownian motion. Then I convolute it. I have to convolve it with gamma 1, so Gaussian and 0, 1. So this now gives me the distribution of B1, and then I push forward it through f, and I have to get measure nu 1, right? So that's the equation, and this equation tells you that if you go back, then you get nu 0. So you start with M1, which is f of B1. You go back, so you take conditional expectations, so you do convolution with gamma 1, and then you hit it with the distribution of B0 now, and that should give you M0, which is nu 0. Okay. So first we did, actually, not first, to be honest, this is the last thing we did, but it should have been the first thing. A sanity check that you do get different models. So if you start with Gaussian marginals, then of course the Bass martingale is the arithmetic case. You should just get Brownian motion back, okay? Because the cost function is 0, so you can't do better than that. So you can't see, but there are 3 lines here. Okay, these 3 lines are just me doing solving the problem and then doing Monte Carlo and checking that the final CDFs are the correct ones. So sanity check. So the problem works, and this surface here is just 1 over x. So 1 over x times x is 1. That's exactly Brownian motion, because I'm plotting the volatility surfaces, the local vols. And then this one is the geometric case. And you see that this is different. So it's a different surface, which if you start with a Gaussian distribution, which will also generate a Gaussian distribution, this is centered at 10, so that you don't have to worry about visiting negative half-line. Okay, and it has a natural smile, right? So you see that you will naturally have a more sort of curvature in the geometric case. But if you fit this to data, so we took a lot of SPX options, I think 11 maturities and a lot of strikes, so you really get full marginals. Then you see that the call option surfaces that you generate are identical, almost. But you would expect this because you have really quite you have to interpolate a quite dense set of maturities, so there isn't much you can do. You will connect everything nicely. But what we haven't tried yet is how the hedging in those 2 models will work. It will probably be different. Okay, I think it's time to stop. So those are the 3 stories I wanted to tell you. I think the bottom line story is that this St. Martingale control dynamics offers a very, I think, powerful way to do projection, non-parametric projection in space of St. Martingales. We use this for calibration purposes. I'd be very happy to hear about other contexts where people can think of relevant problems where you want to do this thing. But the whole methodology works, I think, across range of problems where you have some reference and then a set of constraints, and you want to think about how do you project this reference Ito process onto the set of all Ito processes which satisfy our constraints. And there are some magical cases where you can do this analytically. I think most of the time you have to do numerics. I showed you numerics on the dual side. And while I was thinking of this talk and talking actually to Seb and Silvana, I also thinking there has to also be a way of just doing numerics brute force on the primal side by parameterizing alpha and beta with deep neural nets and putting constraints as part of your loss function and just going for it. I think that should also work, and that's something that we'll probably try next time. But it's probably impossible to prove that it works, unlike on the dual side. All right, I'm not going to talk about this. I'll stop here. Thank you.
Thanks a lot, Jan. Open the floor for questions.